today. So I think others are joining slowly today. Maybe we can have a general discussion now. Okay, till others join. Okay, some minimum number should be there. Maybe up to 10, 6:10 or 6:15. Okay, so we will. I want to have a small discussion. So uh, I think I have presented. I have published a paper on coronavirus. Okay, so I think most of you may be knowing. Just I will we will have a small discussion on that till others come and join. Okay, maybe up to 6:10 or 6:15 we will have a discussion that will be very interesting. Okay, so I have published a paper in sustainable cities and solution. So if you go there, okay, so there you can see my paper. Okay, so in that I have given a graph. Okay, so I have given a graph for spread of coronavirus. Okay, so that is the basis. Okay, so 1 minute, I will just show you the graph. I will show you the paper itself. Okay. So you also can go through this paper. So it is it is an open access only. Okay, it is open access because it is something to do with the corona. Okay, so that is why it is given as open access. Okay, yeah. So this graph only I told. So this graph. 1 minute. I think you may not be seeing this. I will present my screen. Okay. So it will be interesting. Okay, just for a few minutes, we will have a small interesting discussion. Then we will go to our discussion of computer fluid dynamics. Okay. Yes. So are you able to see this screen? Are you able to see the screen?
Yes, sir.
Yeah.
Yes, sir.
Yes, sir.
Yeah. So here I have given. Okay. So the coronavirus transmission potential. I introduced a concept called as coronavirus transmission potential. So this is a psychrometric chart. We have studied the psychrometric chart. We have a dry bulb temperature here, specific humidity here. Okay. So based on from our body, that respiratory droplets will be coming at a higher temperature. So it will be coming at a temperature of around at a saturation humidity. Okay. So that means a very high humidity, and the temperature also will be higher. It will be having our body temperature almost 36, 37 degrees will be there. So that's why I've taken here. Okay, so this is where the respiratory droplet will be there, and the surrounding. Okay, if it is dry, okay, if it is dry like somewhere here, and if it is cold like somewhere here, so the respiratory droplet will dry, and it will become it will lose its density. Okay, so it will lose its density. So because of that, it will become airborne. Okay, so that is why. So in this paper, I have clearly shown that. So in the psychrometric chart itself, I have shown where and all the maximum potential is there for coronavirus transmission. Okay, so the first case is I told a hot and dry climate. So here the potential is high. If you are far away from this location, that is this point, if you are far away, the coronavirus transmission potential is high because of respiratory droplet drying. That is our droplet which you are releasing because of coughing, because of coughing, and because of sneezing, and because of speaking also, singing. So if you are doing that in a hot and dry climate, then from here the potential is very much higher. So that means immediately to droplet will dry. So here trouble is there, and even in cold and dry also. Okay, so in cold and dry also. So this is here, and it is very far away from here. So here also the transmission potential is high, and cold and hot also. Okay, in cold and hot we'll be having heaters in the room. This is because of sensible heaters we will be having this trouble. Okay, so that means cold and dry, cold and hot, hot and dry. In all these locations, I told that the problem will be there. Okay, and now that we have studied about the if you are going up in the latitude, okay, I think we have studied about December solstice and June solstice. December solstice we will be having winter in the northern hemisphere. So according to this psychrometric chart or this information, the coronavirus transmission should be increasing, okay, in the northern hemisphere. Okay, so now I will show you the trend. Okay, I will show you. We will go to the Google and we will see the trend, coronagraph trend. Okay, so the coronagraph trend for Spain. Okay, now you can see it is increasing. Okay, last April it was high, then during summer it was down. Now you are here, you can see now November it is increasing. Okay, and similarly any country in Europe, I can put Italy, because they are going towards winter, no? So winter will be cold and dry, already I told you. So here also you can see now Italy also it is increasing. Okay, and you can put even England also. Okay. So here also it is increasing. Okay, and it is more than April. April they had a peak. It is now it is going more than that. Okay, we'll what are all the countries that are there in the northern hemisphere? So their trouble is there. We'll go for Russia. So now you can see even whatever they had in May, now it is going greater than that. Okay, so that means the expectation is December it will be peaking. December and January it will be peaking as per my paper or my theory. Okay, and even US also you can see. Okay, US also you can see. So rising, 2 waves, and again now also it is rising. Okay, and you can go for Australia. Okay, so what is happening to Australia? Australia, you know, it is in the southern hemisphere. Okay, so they will be having winter during June solstice. So that means let us see what is happening in June. Now you can, it is very clear. Okay, so at the July the peak is there. That is during their winter period. Okay, so during their winter period, the peak is there. The first peak was there during the corona. It was there. Now you can see now it is going on decreasing trend, and even you can go for Argentina. Okay, so Australia the health system is very good, so they have stopped everything. Now summer and the health system, because of that it is remaining constant now. Now you go to Argentina. Okay, Argentina. So this is in the southern hemisphere. Now here you will see it has increased because of poor health system. It has increased. Now it is going on decreasing trend, because here in the Argentina now they will be having summer. Now it is going on decreasing trend. Why the difference is there? The health system in Australia it will be better. Okay, so that is why. But the trend it is going on decreasing. So this is that. Okay, so that means what my in my paper I gave that this graph I gave. Okay, so I predicted that the cold dry climate. Okay, cold dry climate and cold hot climate, cold and humid climate. Okay, the transmission potential will be more. And here you can see when you are switching on your AC, your droplet is somewhere here. When you are switching on your AC, so you will have trouble. So when I told so many people, they were not agreeing. Okay, but now you know everyone is switching off their AC, and even hospitals also they are going on switching off mode in air conditioners. In Chennai, most of the hospitals they are not using AC in the corona ward. Okay, so I think so this paper is a very good paper. Okay, so it is there in sustainable cities. Okay, you can download it. It is free only. Okay, you can just go through that. Okay, because it will be useful if you are in a, other area also. This data will be useful. Okay, so you can see where your climate and what is your transmission potential for corona. I think now you can see for almost all the countries it is matching with whatever I predicted. Almost all the countries it is matching. But somehow this paper I think now I think it will become important. Okay, so by seeing this data you may be understanding this uh, paper will be important. Okay. Okay, so we have 37. I think I hope this should be the strength. Okay, so any doubt is there in this paper, whatever I shown? Any doubt is there? So you can ask. Any question is there? You can ask. Otherwise, we will proceed with the discussion. Okay. So for our case, in the North India, there will be a peak in December. Okay, November, end of November and December, there will be a peaking of corona cases. Okay, so that is possible. Okay, okay, so that is the thing. Okay, we will proceed with our discussion. Okay, so any comment, anything is there? You put it in the chat box. I will. Yeah, you can put it in the comment box. Okay, so the button in the dry air conditioned space, the drying of the respiratory droplet will be happening. So because of that, okay, so the the respiratory droplet can become airborne. Okay, so that is the thing. Okay, so because of that, yeah. Yes, Sanju.
I have one question.
Yeah.
Sir, you said that AC is off. Sir, can you explain one more time why AC is off
No, I don't get you.
in
Yes,
hospitals?
Sanjay.
Sir, yeah, you said that nowadays AC is off for. Hello, sir, I'm audible.
Yeah.
Sir, my question is you said that nowadays AC is off for preventing the spread of coronavirus. Sir, can you explain one more time why AC is off in hospitals?
Yeah, I can do that. No problem. See, just refer to my paper. Okay, so you can see there. So this is the conditioned zone. Okay, so these are all the cold and humid zone, cold and dry zone, hot and dry zone, and this is the room design condition. Okay, so room design condition. So your room design condition is also far away from that only, but it is not as far away like this. Okay, as far away like a cold and humid place or cold and dry place. So when this corona problem was there, the effect was more in Spain and Italy and United States. The reason being, all these countries are in this region. Okay, and you can see the room design condition also. It is not very far away. Okay, so it is not very closer to. If you are in a hot and humid places, the drying potential is very less. That is the concept. If you are see Chennai condition and all, it will be at this point. Okay, so you will be hot in humid places. So that is the thing. And there are one more question. So then how in Chennai number of cases were more? So most of the cases were like AC users, and AC there the respiratory droplet it will be drying because you can see the potential is there. So this much humidity difference is there, and you have temperature difference is also there. So when a droplet is coming out, okay, so in your AC room, it will try to evaporate because the surrounding is dry. It will try to evaporate. So in a AC room, the potential for drying is more. Okay, but it is not as high as this cold and dry climate and hot and dry climate. So that is what I'm saying. You can see in our Maharashtra and other area. Okay, so Gujarat, why the cases are more because it is a dry place. You can see the map of India, climatic map of India. Okay, so these are all dry places. In these places, if you are using AC, still you are making your room drier because you don't have a control on humidity. The AC is running for a few hours, no problem. But if it is running continuously, you are removing the humidity from the room. Okay, so in those places, okay, so the potential for the respiratory droplet to dry, okay, it is higher. So that means that those places can act as a um, the places where the spread can happen, like super spreading, like that it can happen. So you can know even this Tablighi Jamaat incident, it happened in hotel only. Okay, so that means hotel central air conditioning. I can give a lot of examples, but it will go into controversy. Okay, so that's why I don't want to speak too much about this thing. I have analyzed. You can go through this paper. I have analyzed some 100 super spreader events. From that only I arrived at this paper. Okay, so yeah, it is spreading in places where you have a lower setting of air conditioners. Lower setting, if you are going for a very low setting and dry setting. Okay, but because the humidity we are not controlling inside the room. Okay, humidity you are not controlling inside the room. So what will happen? The AC will run for some time. After some time, what will happen? Again and again, the humidity will be removed. So the dryness of the room will be higher, or in other words, humidity will be going lower. So somebody is breathing there inside that room. Somebody coughing or sneezing inside the room. The droplets will become dry, and this dry thing it will spread. Okay, so it will lose its density, because from liquid the water density is 1000. It is going to steam. It will be 1/1000. So because of that, what happens? This steam or the vapor, it will try to float in the air. So that will help in super spreading or spreading. Okay. So that is why this I have observed. Okay. So in most of so many cases I have studied. Okay. So I observed, but I didn't come out. Okay, because it will create some trouble. But just now I told you it is very you can understand very easily. So in now in Scandinavian countries, US and Russia. So now they are going into the uh, winter that is cold and dry region. So that means the cases are increasing. Okay, the reason is cold and dry climate. Respiratory droplet will evaporate, and it will spread. Okay, spread. So that means the potential for spreading it will be higher. So that is what I call it as the potential for spreading. Okay, so that will be higher. Okay, in the climate. Okay, so I think it is a common topic. A lot of controversy will be there. So I don't want to go. Okay, so I call it as coronavirus transmitted potential in various climates. Okay, so I discussed very detailedly. So please go through this paper. Okay, so if you want, you can have a discussion afterwards also. Okay, no problem. I think this discussion would have been useful for you. We will go with our regular discussion now. So I think almost I have the regular attendees are there. Okay, fine. Thank you. So yeah, so we will. So once again, I welcome you for this ninth day. Okay, so the topic today, what we are going to discuss is the basics of computational fluid dynamics. So in general, we are going to study about the general numerical science. Okay, so the numerical science of computational fluid dynamics. Okay, so we will go step by step. Okay, first we will. Okay, so these are all the objectives what we are going to discuss. Okay, so we are going to discuss about 1D, 2D, transient, all types of simulations we are going to discuss today. And what are the types of solutions? Okay, since we are going for CFD and the numerical solutions, so we have to know about what are all the types of solutions that is possible. So the types of solution that is possible is the experimental solution, analytical solution, and numerical solution. So any problem we will be having a governing differential equation. Okay, so what are all the governing differential equations for CFD that we are going to discuss? Okay, so for time being, we will take our energy equation, which is very known to us, because we solve the energy equation only for the our energy simulation softwares. So you take the energy equation, okay, Fourier conduction equation, transient Fourier conduction equation. So this is an energy equation. So that means how you can solve this energy equation. So the energy equation can be solved, okay, experimentally. So that means you can take a rod and you can find put the sensor and find the temperature. Or similarly, inside the air conditioned room, you want to find out what is the temperature, okay, inside the room. So you can put lot of sensors inside the room, okay. So and then you can find out what will be the temperature at various places. Okay, so that is the experimental solution. Okay, now what you want, what you can do that in the same room. Okay, if you want to find the temperature distribution, so you can write the governing differential equation, and you can find out uh, what will be the boundary condition, and you can find out what will be the analytical solution for it. So what is the analytical solution? The analytical solution is an integral solution. So you take the equation and you will try to integrate that. Okay, so whatever the solution you are getting, so that is called the integral solution or analytical solution. For example, this is a sphere, so this is the equation. Okay, so equation for conduction of a sphere. Okay, with the heat generation. So when I try to integrate this equation and apply these boundary conditions, so I will be getting this solution. So this is the temperature distribution along the radius, and this is the heat transferred along the radius. Okay, so this is what we call it as the solution. So that means inside the domain. So this is the domain. I have the solution for all the places. Okay, I have the solution for all the places. Similarly, I have the heat transfer also for all the places. So that this I call it as the analytical solution. So analytical solution, you are very familiar. You would have studied these things in your basic course on heat transfer. Okay, so all of you might have studied a basic course on heat transfer. So in that, all of you might have studied about analytical solution. Okay, so that is what are all the solutions you are having in your data book. So you would have had a data book by CP Godandraman. Okay, heat and mass transfer data book by CP Godandraman. All the solutions given inside that. Okay, so those are all analytical solution. Those things are got by integration of the governing equation. Okay, so if it is equation is the Cartesian coordinate system, so we will be taking the equation in the Cartesian coordinate system, and then we will be trying to integrate it. So when I integrate it, I get the heat transfer through a slab, heat transfer through a cylinder, heat transfer through a sphere. Okay, so like that we get all the solutions. So we get the solution from the data book, and we try to use that. So that is called analytical solution. So but still we are going for numerical solution. Okay, so we are taking a numerical solution. What is numerical solution? So we are going to take the domain. I am going to divide the domain into number of regular shaped subdomains. So each subdomain I am going to call it as the mesh or the grid. Okay, so in each grid I am going to convert the governing differential equation into algebraic equation. Okay, so for each grid I am going to have one algebraic equation. If I start solving this algebraic equation, I am going to get the solution. Okay, so that I am going to get the solution for the full domain. Okay, CFD is a numerical solution. Your finite element analysis is a numerical solution. Okay, so these are all numerical solutions. So wherever you are going for modeling, and going for meshing, and then if you are doing the boundary condition, and after that if you are getting the solution, so that is the numerical solution. Okay, so already I told you what is the solution, or what is the solution. It is your analysis or finding the solution. It is the response of the domain for the external excitation. So if I take that here, so this is the domain. So we are giving we are trying to find out what the response of the domain to the external excitation. So what are external excitation? These boundary conditions are external excitation. So what is the response of the domain? If the boundary condition is like this, then the temperature distribution will be like this, and the heat transfer will be like this. So that is the response of the system. So I have a system or domain, and I am giving the external boundary condition. So that is external excitation. So the answer what I am getting, okay, temperature distribution and heat. So that is the response of the system to the external excitation. Okay, so that means for a problem, for a CFD problem or a numerical solution problem, what are all the parameters that will be there? So I should have a domain. Okay, so that should be a body, and for the domain I'll be having the equations. So what is the equation? Equation is the governing physics of the problem. Equation is the governing physics of the problem. See, in the same body, if I'm giving a heat transfer equation, it will give me a temperature distribution solution. If I take the same body, if I'm using it for a force boundary condition, okay, I'm giving a force, external force, then it will give me the stress distribution, deformation and stress distribution. So that means the water body is same type of meshing, but equation is different. So that means physics is different. So what is the equation? The equation is the one which tells you about the physics of the problem. Okay, so if you go for a CFD problem, so you will be having a continuity equation, okay, which is the conservation of mass. So you will be having the momentum equation. The momentum equation is the conservation of momentum. Okay, and then you will be having the energy equation, so which is conservation of energy. So each equation it is telling something about the physics. So even you can have a mass transfer problem also, you can have a mass transfer equation also. So that means one more physics is added, that is mass transfer. So each equation represents one physics. So that is what I am underlining, that each equation it is representing the physics. If energy simulation software, whatever you have studied, we have considered only one physics. It's very simple. That is thermal energy conservation. So energy conservation equation. So we are solving the thermal energy conservation equation. So we are getting the solution. Okay. But in the same domain, I can have 3 or more physics or 4 or 5 physics also. It is possible. How it is possible? If I am going for CFD, this is possible. So conservation of mass, one physics is there. Conservation of momentum in x direction, y direction, in z direction. 3 equations. So totally 4 equations. Conservation of energy equation, 5th equation, and conservation of a species equation. So 6th equation, turbulent kinetic energy equation. 5th equation, turbulent dissipation equation. 6th equation. So that means six physics are there. So that means in a simple problem, it is possible to get 6 physics or 6 equations. Okay, so that is very common in CFD. Okay, so now I think you would have been understood very clearly that each equation represents a physics of the problem. Okay, so now next we will go. Okay, now in this class we will have a detailed discussion on energy equation, because you know energy equation already. We have solved the energy equation already, and from that we have tried to find out what is the solution for this. Okay, what is the solution for the problem? Okay, or we have done the FDM form, or we know something in basics about the energy equation. So what we are going to do? So we are going to discuss everything with respect to energy equation. So that is a heat transfer equation. So from there we will try to understand other equations in the CFD. Okay. Okay. So now we will go to the equation. So when I go to the equation, okay, so this equation I call it as the energy equation. Okay, so this equation I call it as the energy equation. Just 1 minute. Okay. So hope the screen is visible for everyone. Okay. So any trouble is there? Please tell me. Okay, so this is the energy equation. So this is I call it as the general transport equation. Okay, so this is the general transport equation. So the first term, okay, so in this general transport equation, this term is called as a transient term, rho dou rho h by dou t. So this is nothing new to you. So in the Fourier conduction equation, you would have had a term, okay, which is called as this one. So that is dou rho Cp t by dou t. So the same thing only it is given. Cp into t is h. Okay, so that is what is given. So this is transient term. So this is the transient term. Okay, this is the transient term. Okay, for energy. So then I have the convection term. Okay, so then I have convection term. Convection term it is given as a dive of rho hv. Okay, so v is so don't worry about the dive rho v h and all. So regarding this we are going to study. V is the velocity vector. So V is ui plus bj plus wk. So all the 3 velocities will be there. Okay. So when I take divergence of this vector, okay, rho hv, because V is the vector. So this is a dot product. Okay. So I have dou by dou x of the x component is rho u cpt. Then I have dou by dou y of rho v cpt and dou by dou z of rho w cpt. Okay. So this velocity, since velocity is there, so this term it is called as the convection term. Okay. So here you can see u velocity is there. Here you can see v velocity is there, and here it is w velocity is there. So that is why it is called as convection term. So what is convection term? Okay, so okay, now I will complete this and again I will come back. So this is called as a diffusion term. So dive of k grade t, it is called as diffusion term. So what is dive? I dou by dou x. Okay, so dive is I dou by dou x. Okay, so dou by dou x plus j dou by dou y plus k dou by dou z. So that is how I am going to have. So dive is dot product of this. Grade t is a vector. Okay. So when I take dot product of this, I will be getting dou by dou x of k dou t by dou x plus dou by dou y of k dou t by dou y, dou by dou z of k dou t by dou z. Then I have the source term. Okay, in energy I will be having a viscous heating component, that also I am having. Then pressure volume. Okay, so minus dou p by dou x, the pressure gradient term in x, y, and z, and with the volume. Okay, so I have a minus p dive of v velocity, So this is a pressure term. Okay, the energy component of the pressure term. Okay, so I have the transient term, so which is given as dou rho cp t by t. So this is the term, and I have the convection term. So the convection term, it is given by dou x of rho u cp into t, dou by dou y of rho v cp into t, and dou by dou z of rho w cp into t. Okay, so this is convection term. If velocity is 0, okay, so if velocity is 0, there will not be any convection term. Okay, so the convection will not be there. So physically also, if there is no velocity, convection will not be there. Okay, but diffusion will be there. And this is like conduction. So conduction is diffusion heat transfer. Okay, so in the CFD we call this as diffusion, but this is actually, it is conduction. What is conduction? It is the molecular diffusion. Okay, so it is a molecular transport. So even without velocity also this can be there. So that is why in solid this thing is there. In solid this thing is there, but this will not be there. In solid this will not be there. Why? In solid there will not be any movement. Okay, so there will not be any flow. Okay, so if there is a movement or flow, then only this convection term will be there. Okay, and this is called the source term. Okay, now I will go one step further to explain this equation. Very simple, because in subsequently we are going to discuss about all the equations. So this is the first step. We will try to understand what is this equation. So this term, okay, so this is called as a transient term. So what is a transient term? Okay, so think that what is a transient term in energy? Okay, we are all air conditioning people. We will try to understand from the air conditioning perspective. Suppose you are switching on the air conditioner. Okay, so we'll consider a fluid air inside the air conditioner room. Okay, so I am switching on the air conditioner. Okay, when I switch on the air conditioner, immediately I will not get 25 degrees inside the room or 24 degrees here. Set point I will not get immediately. Okay, so air conditioner has to run for some time. Maybe 5 minutes it has to run. Then only in all the place you will be getting 24 degrees centigrade. Okay, before that it will be 30 degrees. So that means from 30 degrees, as I switch on the air conditioner, slowly the temperature in the room will be increasing. So that means this dou t by t, that term will be there. Okay, dou t by dou t, that term will be there. It is not equal to 0. Till what? So if I am taking a point at the center of the room, okay, so before switching on the air conditioner, everywhere it will be 30 degrees. So that means that dou t by dou t is 0. So that means that dou t by dou t is 0. So what is the meaning of dou t by dou t is equal to 0? It means that it is a steady state. So that means before switching on the air conditioner, I have the steady state. Everywhere inside the room it is 30 degrees centigrade. Okay, then I am switching on the air conditioner. So that means then the air conditioner starts. So from the room temperature, it will be dropping from 30 degrees. Slowly it will be dropping to 24 degrees centigrade. So in the process of dropping, in the center of the room, this dou t by dou t will not be equal to 0. It will have a negative value because the temperature is decreasing with respect to time. So that means this is not equal to 0. This value will be there. In other words, that is where transience is. So when transience will be, so when you are going from a steady state, okay, when you are moving, when you are disturbing a steady state, so you will have transience. Okay, so then what will happen? So from 30 degrees, the temperature will be dropping up to 24 degrees centigrade. Then what will happen? Continuously, it will be trying to maintain 30 degrees inside the room. Okay, but there will be a thermostat cutting off if you are having an on-off control. So there will be a thermostat cutting off and switching off of the compressor. That is possible. But if it is not there, okay, so continuously you are maintaining, because you are having a proportional controller and continuously you are maintaining that 24 degrees inside the room. Then what will happen? Now when if you take this dou t by dou t, okay, now what is happening? Now again this is equal to 0. So that means the room has reached the 24 degrees centigrade. Then also this is 0. So that means now steady state is reached. So that means before switching on the air conditioner, steady state was there. Okay, and after running the air conditioner and reaching the temperature, again steady state is there. So it means when starting from 30 degrees, when you are reaching for 24 degrees, so at that point of time, the temperature is varying inside the room. So that point, this thing will be there. So that means this transient term will be there only at that time. So the meaning is that this term will be there only if you are moving from one steady state to next steady state. Okay. So on the way you will be having transient. But if you are reached the steady state is the energy balance condition, perfect balance condition or equilibrium condition. What is the meaning? The energy removed from the room is equal to energy entering into the room. So that is steady state. So that means it will maintain a constant temperature inside the room. So at that point, this I'll be having the steady state. So at that point, only dou T by dou T will be 0, and other when you are starting the equipment, this will not be equal to 0. In fact, it will be negative. And again, when you are switching off the air conditioner, what will happen? Suddenly, the room will not go to 30 degrees. So slowly, from 24 degrees, the temperature will be increasing. Okay, and after that, again, it will be reaching 30 degrees. Okay, throughout. So that means when you are going from 24 degrees to 30 degrees, on the way, this transient is there. So on the way, this transient is there. So that means transient will be there only when you are starting the equipment and when you are stopping the equipment. So that is why when you are doing an experiment in the heat transfer lab, they will tell you just wait for some time. Okay, just wait for 10 minutes. Okay, you wait for 10 minutes. After that, you take the reading, because the solutions you are having in your data book or in your laboratory manual, it will be steady state solutions. You should not take the reading when the process in transient. So that means your calculation will be wrong. Okay. So what is the meaning? So this will be there only when there is an imbalance. Okay. Similarly, when I was talking about a wall also, when there will be unsteady state. Okay, whenever the heat entering is not equal to heat leaving. Okay, so then only transients will be there. So if there is a balanced system, there will not be transients. Okay, so that is why when you are starting and stopping the equipment, the transients will be there. Similarly, when the compressor is on or off, that is sometimes because of thermostat setting. So the compressor will be on and off. So at that point also there will be disturbance in the temperature inside the room. Okay, so that point also transients will be there. Okay, so in steady state transients will not be there. When you are moving from one steady state to the next steady state, on the way you will be having transient. Okay, so my explanations will be different. It is from the experience, but if you think you will understand this. Okay. Okay, so then I have convection and diffusion. What is diffusion? What is diffusion and what is convection? So when you know why the heat transfer will be taking place, how or in a fluid. Okay, when I'm considering a fluid, uh, how the flow is taking place or what is the effect of flow. Okay, when or how the what is the effect of flow or the effect of energy, effect of temperature, because my variable in the energy equation, it is T only. Okay, so here my variable is T, because everywhere it is T. When I solve the energy equation, I will be getting the solution for T only, temperature distribution only. From that solution, I will be getting the heat transfer. So that is different. But what is my variable? It is T only. Okay. So that means the property is T. The property T is transported. Okay, in a fluid. So how it is possible to transport? It can be transported by diffusion or it can be transported by convection. Okay, so if it is transported by convection, okay, so this term will be predominant. If it is transported by diffusion, so this term will be predominant. So what is the transport by diffusion? So transport by diffusion, it is by conduction. Okay, so when you think that some heat source is there, okay, somewhere a heat source is there, and from there the heat is diffusing. So the heat will be diffusing equally in all the direction. Okay, equally in all the direction. So that is the property of diffusion. Okay, so the spread of information, the temperature will be transported equally in all the direction. For example, you think a cylinder. Okay, at the center you are having a hot fluid. Okay, so you take a cylinder. If I am having a hot fluid, so at the center I am having the hot fluid. So how will be the temperature distribution? So the temperature distribution from there, it will be coming like this. So if you do it on the other side, it will be going like this only. So what is the meaning? The meaning is that the information is transported equally in all the directions, even go in the other direction, forward and back also. So it will be equal only. So that is the nature of diffusion. So in diffusion, the information will be transported equally in all directions. There will be no physical movement. There will be no physical movement. So that is what I call it as the diffusion. Okay. What about convection? So in convection, the flow should be there. Velocity should be there. Whenever velocity is there, then convection will be there. If velocity is zero, there is no convection. So what is the definition of convection? So this is the definition of convection. Okay. So what is convection? Heat transfer. Whenever flow is there, if you are able to transport the property temperature from one place to another place, so that is called as convection. But if you are asked to define the same convection in heat transfer, you will be defining it differently, and you will be involving the heat transfer coefficient, and you will be telling wall surface fluid like that. But the real definition of convection is, if velocity is there, convection will be there. Okay. So if velocity is there, flow will be there. So the flow of fluid will be transporting the property temperature from one place to another place. So that is called as convection. So the best example for this is our air conditioner itself. So in the air conditioner, we will be having a low temperature. Okay. So what is happening, from the air from the room, it is going towards the air conditioner, and it is picking up that low temperature and it is taking into the room. So this is convection of the property temperature. Okay, convection of the property temperature into the room. Okay, so if there is no flow, is it possible to transport the heat? No, it is not possible. Or for example, if you want to have a further understanding, so think that a heater is there. Okay, you think of a winter air conditioning system. So a heating system is there. So from the room, it is picking the cold air. Okay, so it is going to the heater. So from the heater, it will pick up high temperature. So that means from the heater, it will take the high temperature information and it will go into the room. So that is called as convection. Okay. Or you take the other example is that you have some place where, okay, for example, Ooty is there. At Ooty, if it is raining, okay, so from there the cold water is moving from the top towards the metropolis. So that means the cold water information is transported from that place to this place. It is purely because of convection, because of fluid flow. Okay, so that means a low temperature or high temperature from one place, if it is transported to the another place because of velocity, that is called as convection. Okay, so if velocity is zero, then there will not be any convection at all. So that is convection. Okay. Diffusion, it is molecular movement. Okay, it is molecular movement, molecular transport. So there will not be any actual movement under. Okay, so that means in fluid, is it possible? Yes, it is possible. You take a stagnant fluid, if the temperature information is transported without any movement, if the temperature information is transported purely because of the thermal conductivity of the fluid, so then it is conduction, or then it is diffusion. Okay, but there should not be any movement. If movement is there, then it will come under conduction, either natural convection or forced convection. Okay. Okay, so now I think I hope you would have understood about what is convection. Then you would have understood about the diffusion, because in heat transfer or in CFD, all these things are very important. So we have to know about all these things. Okay. Then we go to the last term, which is called as the source term. Okay. Source term. Okay, so you can consider anything as a source. For example, you are studying about air conditioner. So in air conditioner, in a heat load, we have considered that each person is emitting heat inside the room. Okay. For example, I will be emitting a latent heat and a sensible heat inside the room. Okay. So that means what is happening? I am a source. Okay. So when I am solving the equation, so when I can model myself, and from this place I can give that heat is generated. 120 watts heat is generated continuously from when I am inside the room. Okay. So then it is called as the source. So inside the domain where you are modeling, if there is a heat source, you can put it here. Similarly, not only heat source, there can be sink also. Okay, there is some cooling equipment is there inside the room, or something which is absorbing heat. It is there inside the room. So then it is called as the sink. So a source is also possible. When it is plus, it is called as a source. When it is minus, it is called as the sink. So you may be thinking, what sink it is possible? Okay, what sink is it is possible inside the room? Okay, something which is removing heat from the place. Okay, for example, a refrigeration system is there which is absorbing heating from the room. Okay, or you are keeping the refrigeration equipment open, a refrigerator you are opening. So what will happen? Suddenly in that place the heat will be absorbed. Okay, so that is so similarly if I am having some hot source inside the room, so that is so if this source term is plus, then it is uh, heat is added inside the room. If the source level is minus, heat is removed from the room. Okay, okay, so I have studied about diffusion, I studied about convection, I have studied about the uh, various terms. Okay, so now uh, if I am going for CFD, this full equation will be required. Okay, but if I am going for studying about the solids, okay, solids, so then this term is not required. Okay, so this term is not required. Why this net term is not required? Because in solid the domain will not be moving. For example, if you think you take some solid substance, okay, then some solid substance, for example you take our wall itself. Okay, you are studying about heat transfer in the wall. Okay, yesterday you are studied about heat transfer in the wall. In the wall there will not be any movement. Okay, so but if you are trying to solve a problem for a heat transfer in the wall, then you have to drop this term. Okay, so then you have to drop this convection term. Okay, in fluid only we will be having this term. Okay, when fluid flow is there, this term will be there. But if you are going for solid, if you are going for analysis of the solid, this term will not be there. Today I am going to drop this purposely because I don't want to give you a complication in day one itself. Okay, so I'm just dropping this term. Okay, you think that we are going to analyze solid systems only in your energy simulation solver. Already I told that we are discussing about the solid systems only, that is wall, window, door. Okay, and other type of systems. So those are all solid systems only, and that too it is one dimensional. It is very simple and convenient for us. Okay, okay, so that means that now you know this system is transient system and this is diffusion, and only this is for three-dimensional diffusion. That means if you are considering a volumetric domain, then I go for this. And heat will be transferred in all the three directions. Even a wall is a volumetric domain, but heat will be flowing normal to the wall only. It will not flow in other directions. Heat will flow into the room normal to the wall. So that means you will consider only one direction only. Okay, one direction only. Other directions will be neglecting. Okay. On the contrary, if the heat is flowing on all the three directions, I have to consider all these things. And the source, already I told you, source is the generation of heat, okay, per meter cube. What is the unit of this equation? It is watt per meter cube. Okay, so just try to work out. It will work out as watt per meter cube. Okay, so source is in watt per meter cube, and this equation is watt in per meter cube. Here you can see it is MCP del T, but the rho only is there because it is in watt per meter cube. Okay, when I multiply volume, then it will become watts. Everything throughout it will become watts. Now, what is happening in a steady state? Okay, in steady state, I told dou T by dou T is 0 and dou T by dou T is 0. What is the steady state? Air conditioner is running. In running condition, the room distribution is constant. Room air distribution is constant. That is steady state. Similarly, before the air conditioner, throughout the room, you had 30 degrees centigrade. So that is a steady state. So if you want to find the temperature distribution for that condition, then you have to use this equation. Okay, so that you have to take that dou T by dou T is 0, and with that assumption you have to mark this. So that means if the source term is not there, suppose source term is neglected, okay, that is possible. Okay, so this will be my equation. If it is a two-dimensional, this will be my equation. So this will be dropped. If it is a two-dimensional, this will be dropped. If it is a one-dimensional equation, this is the equation. This you might have studied in your basic heat transfer. First class you would have studied a steady state Fourier conduction equation. Okay, but we are not. We will have a discussion on steady state as well as we will be having a discussion on transient also. This equation is not new for you. So we have discussed already about this thing. Okay, so this class we will have a discussion on this and this equation. Okay, how general discretization will be proceeding. So that is what we are going to discuss. Okay. Again, we will go back. What is computational fluid dynamics, or what is numerical heat transfer? Numerical heat transfer, it is you for all these type of problems, you will be having a domain. Okay, so all this domain, that is a domain is what the volume you are considering for the analysis. Okay, So what is analysis? The response of the domain for the external excitation. What are all the external excitation? External boundary conditions. Okay. So you will be having a governing equation for your problem. Okay. So that governing equation tells you about the physics of the problem. For example, if I'm going to solve the equation what we are having now, so it is heat transfer physics. So when I solve this, I'll be getting the answer response corresponding to heat transfer only. The response will be temperature distribution or the heat flow. So that only I'll be getting here. Okay. So now if I am going for momentum equation, so the physics is different. There I'll be getting velocity distribution. If I am going for the continuity equation, so I'll be getting pressure distribution. So how we will discuss afterwards. So similarly, mass transfer, species transport equation, I'll be getting the species distribution plot. Okay. So this concept you have to register in your mind. Okay, in CFD, if you want to understand CFD, so these concepts you have to register in your mind. Okay, so now okay, so we have the different type of solutions. Okay, so we have a different type of solution. Now that I have discussed about the equations, a simple question. So when I told there is an exact solution, there is an integral solution. When there is integral solution, why you are going for numerical solution? Okay, so that is a natural question anyone can ask. Okay, so when there is a integral solution, so why we are going for numerical solution? Okay, so the problem is like this. So the actual your physics of the problem is that you will be having a oval shaped body, but your exact solutions you will be having only for sphere. Okay, then what you have to do? If you want an exact solution, then you have to take this and you have to solve and you have to do. There will be a lot of things. You will be having eccentricity, major axis, minor axis. With that, you have to put all your solution, and it will be like a PhD work. Even finding the solution for this will be like a PhD work for you, and you don't have the solution. But if you go for a numerical solution, what is happening? You are going to divide this domain into number of regular shaped subdomain, and for each subdomain, you are going to solve this governing differential equation, which we have seen just now. And when I am going to solve that, I am going to get the temperature distribution inside the domain. That means in exact solution, I don't have an answer. I have the answer only for the sphere. That is also approximate. But on the contrary, in a numerical solution, I am taking the same shape, okay, but I am going for a numerical solution. I'm converting that governing differential equation into algebraic equation, and I am solving those equations. There also some amount of accuracy is there, but it is far better than having the actual shape. Okay, going away from the actual shape. It is far better than going away from the actual shape. Why? Because in reality, okay, so leave alone this building heat transfer. If you are going for any heat transfer and it's any CFD solution, in reality, all your components will not be regular. Okay, so it will be irregular only. Okay, for example, you take all the automobile components from the connecting rod to all your spare parts. Okay, if you are going for analysis, all those components will be having irregular shape only. So that means having solutions, exact solution for all these things will be difficult. The best possible thing is you just draw this shape, model that, mesh it, and convert those equations into algebraic equations, solve it beautifully, you will get the solution. So that means you are having a numerical solution for your problem. So that is why we are going for numerical solution. Okay. So the next is how we are going for numerical solution. Okay, finite difference method. What is finite difference method? We will take our own things. Okay, so we have the domain. Okay, so we have taken it is a one-dimensional domain. Okay, so this is my one-dimensional domain. Okay, so in the one-dimensional domain, so you think it is a temperature distribution in the one-dimensional domain. That means you have a wall. In the wall, I am having a temperature distribution like this. Think that this is outside the wall and this is inside the wall. Okay, so what is your solution? This f of x is like a t of x only. Okay, now I want to find, okay, so from this, I want to first define what is the finite difference method or what finite difference solution. Okay, so what is that we are doing? So from a particular point x, so this is the domain. X is the domain. One dimensional means x is the domain. Okay, so this is a t of x. This is the solution. From this point x, I am taking a distance delta x. So this is that delta x. After that delta x, okay. So after that delta x, I am trying to find the next point. Okay. So what is that? It is f of x plus delta x. that is f of x plus delta x. So from this, I am trying to find out what is dou f by df by dx. Okay, so df by dx, it is given here. So by definition, it is, you know, it is delta f by delta x, limit the delta x tends to 0. So this is mathematical definition of dou f by dou x. Okay, but so in what is the definition? It is f of x plus delta x. So that is this value. What is this value? F of x plus delta x minus f of x. So this is f of x divided by delta x. Okay, so this is f of x plus delta x. This is f of delta x. That is, I call it as delta f. So this is delta f divided by delta x. So I am getting this. Okay, so dou f by dou x. So I am getting this. When the limit delta x tends to 0 means if it is infinitesimal. So when it is very small, okay, I can do the differentiation. Dou f by dou x, dou f by dou x is defined. Okay, but if this dou f by dou x is very much larger, if it is higher, then this is not defined. Okay, this is not defined. That is, this component is not defined. So what is that? What is that I have to do? So it means this you have to remove. Okay, if you are removing this delta x tends to 0, it is not going to be there, because in all your domain you are not going to have an infinitesimal delta x. You are going to have a finite delta x. Okay, so you should know. So if you have a domain of 1 meter length, so if you are dividing that into 10 divisions, so you are going to have 10 centimeter, 10 into 10 centimeter divisions. So it is not infinitesimal, it is finite. So that is why it is finite difference. Okay, so what is finite difference definition for dou f by dou x? It is f of x plus delta x minus f of x divided by delta x. No delta x tends to 0. If it is there, then it is, I am calling that as a finite difference. And how if it is dou f by dou x, okay, or if it is dou t by dou x, so it is t at this value minus of t at this value divided by delta x. So that is what? So that is t at this discrete point. Okay, so this is t at this discrete point. Similarly, t at this discrete point. So when I find the difference from that, so that is how I define dou f by dou x. So dou f by dou x, I can find out using Taylor series expansion. Okay, so that you can find out from the definition of f plus delta x, and similarly x minus delta x, I can find out various derivatives. Okay, why we are finding derivative? Because in our governing equation, okay, in our governing equation, you are having everything in terms of, just now we have seen the equation. I am having in terms of dou t by dou x or dou square t by dou x square. Sometimes it is possible that we can have dou square t by dou y dou x. A mixed derivative is also possible. So that means for all these expressions, dou t by dou x, dou square t by dou x square, so you should have a equivalent algebraic expression. So that is the objective of our doing this work. So that means for all their partial derivatives, I should have a equivalent algebraic expression. Okay, so that is what we have to do. That to be what we do it in finite difference method. Okay, but here it is interesting. Okay, so it is interesting here. Here we are having. Okay, so here we are having. Okay, so here we are having. We can derive this expression very easily by energy balance method itself. And this I have done already to you. Okay, this I have done already to you. So again, you can consider. So this is the see, all these things are in PPT. Okay, so don't worry, it is there in the PPT. You can see. Just I am giving explanation of whatever it is available in the PPT. Okay. So now I told it is the wall. Okay, it is a wall. You think that the wall heat transfer is taking place outside. This is outside the wall, and this is inside. So there is a temperature distribution is there. Okay, so now what is that? For dou square t by dou x square, I require a equivalent algebraic expression, or for this equation, for this differential equation. I should not tell that it is partial differential equation. For this differential equation, okay, for this differential equation, second order differential equation, I should have an algebraic expression. Okay, so that is what we are trying to find out. Okay, so for first order we have found out it is just a temperature difference by delta x. Just now we have seen. Okay, for second order we have to find out how that we are finding. Okay, very important. Just note here. Okay, so this m, it is the node under consideration, or node for which we are writing. Okay, m is the node for which we are writing. What is the volume of m? So this is the volume. Okay, so this is the volume of the m. Okay, so this is the volume. Okay, so I think throughout the wall, this is the volume. Okay, this is the phase. Okay, and this is the next phase. So what is the value at the face? It is m plus a half here, and this is m minus half on the other side. Okay. So very clear. Okay. So very clear. Okay. So it is very clear. So your phase is there here. Okay. So this is your phase is there here and here. That is m plus half and m minus half. Now I am trying to find out the differential at m plus half and m minus half. I am trying to find out the differential at m plus half and m minus half. Okay. So the differential at m plus half. So that is at this point. We should know this is continuous solution. We are going to divide that into a numerical solution. So that means I have three grid points. It is m plus 1 and m minus 1. Okay. Now what I am doing, so at this m, I am trying to find out what is dou t by dou x at m plus half. So dou t by dou x at m plus half, that is at this point. Okay, at this point it will be t m plus 1 minus of tm, em plus 1 minus of tm divided by delta x. This distance is delta x. Okay, so that is what I have it here, tm plus 1 and minus tm divided by delta x. So that is what I have it here. Similarly, when I go to m minus of, at this point I try to find out it is tm minus tm minus 1 divided by delta x. Tm minus tm minus 1 divided by delta x. Okay, and for the node we are trying to find out the difference. So that is dou square t by dou x square. What is dou square t by dou x square at m? It is difference of difference. So this I can write it as dou by dou x of, or d by dx of dt by dx. So that is how I write it. So sorry, this is d. Okay, 1 minute. Okay, so it is d by dx of dt by dx is equal to 0. Already I think I told you. So that means the dt by dx is constant, or dt by dx at east minus of dt by dx at west. This concept I told you already. Okay, so I told you that already. So that is what is happening. Okay, so this is what is happening here. Okay, so that means, so what I am having here. Okay, so what I am having here is dou t by dou x at this point minus of dou t by dou x at this point. Okay, at m plus of minus m. So it is this we have done already. So when I do that, what I am getting, this is dou t by dou x at m plus half. This is dou t by dou x by m minus half. When I simplify this, okay, so this delta x will come on the denominator. So it will become tm minus 1 plus tm plus 1 minus 2tm. So this is actually the definition of dou square t by dou x square. So what is that we want? So we want what is for, I want an algebraic expression for dou t by dou x. I have it here. Similarly, I have an algebraic expression for dou square t by dou x square. I have it here. So when I will go to the governing differential equation, wherever dou t by dou x is there, I can have this expression. Similarly, wherever dou square t by dou x square, I can have this expression. Similarly, I can find an equivalent algebraic expression for dou square t by dou x by dou y also. So that is possible. Okay, so from that I can find out what will be my solution. Okay, so I can find out what will be my solution. Okay. Okay, so now I have it. Okay, so I have it. Now this is okay. So now on that basis, so what is dou square t by dou x square? Very simple. Okay, so what is dou square by dou square? The node under consideration will get minus 2tm. So tm plus 1 plus tm minus 1 minus 2tm divided by delta x square. So that is what I have. Dou square t by dou x square. It is tm plus 1 plus tm minus 1 minus 2tm divided by delta x square. So that is how this equation. Now we have seen that this governing differential equation. Just now we have seen that this has become this dou square t by dou x square. I am converted into this. Okay, I have substituted this. So now you know this is a differential equation, ordinary differential equation. I have converted that into an algebraic equation. When you are trying to solve this problem, it will be like t1 minus 2 t2 plus t3, like that it will go. So that means if I go for the next one, it will become 1 will become 2, this will become 3, 4, next one 4, 5, 6. So for each equation I am going to have an algebraic equation. So that means I am going to, if there is a wall like this, I am going to get a series of linear algebraic equations. Okay, with the 2 terms. If you are going to solve for a one-dimensional problem, you are going to have 3 terms. So that is what we have to understand. Okay. Now, if I am going for a wall, okay, so if I am, the wall will be like this. So wall will be like this. So from that, this is my governing differential equation. This is my governing differential equation. This is my algebraic equation. This algebraic equation already I told you I am going to have it for all the nodes. Okay. So again, I go back. What is the definition of CFD, or what is the definition of numerical solution? CFD or numerical solution, you are going to divide your domain into number of regular shaped subdomains. For each subdomain called as nodes. For each node, I am going to have governing differential equation. I am going to convert that governing differential equation into algebraic equation. So this is my differential equation, and this is my algebraic equation. This algebraic equation, it is going to be there for 0, 1, 2, 3, 4, 5, like this. For all the things, I am going to have this algebraic equations. Okay. So these algebraic equations, I am going to. So that means I am going to have system of matrix. Okay, linear algebraic equation. So here you can see it's the same wall. I can do the discretization like this also. That means the number of nodes is higher. So that means more number of meshes there, or more number of nodes are there. Okay. So this is also possible. That means that how many number of nodes are there? So many number of equations, algebraic equations are there. Here I am going to have 6 means I am going to have 6 by 6 matrix, or 6 algebraic equations will be there. If I am going to have 100 algebraic 100 nodes, 100 by 100 algebraic equation, I mean 100 algebraic equations are there, the matrix is going to have 100 by 100 size. So that is what I have to understand. Okay. Similarly, I can do the discretization of two-dimensional problem also. The same discussion I can extend, because now you are going for CFD. CFD is not about one-dimensional. Only your energy simulation is one-dimensional. CFD is three-dimensional. Okay. So that means we should know for 3-dimension also. So this is my two-dimensional Fourier equation. Steady state two-dimensional Fourier equation. So I have dou by dou x of k dou t by dou x plus dou by dou y of k dou t by dou y plus E by K. Heat generation term is also there. So this also I can you can discretize when okay, in a two-dimensional, my domain is going to be an area. If you remember, I told in a one-dimensional problem, I told my domain is a line. Here you can see my domain is a line. Okay, but in a two-dimensional problem, my domain is not a line; it is an area. Okay, and I have x and y also. Okay, my solution also I will be having x and y. So I am going to divide the area into a number of small areas. Okay. So there also I will be having the grid points. I am going to solve the problem for the grid points to get the solution. So for dou x of k dou t by dou x. So this is this algebraic equation. Now here you can see the change. There you had m plus 1, m minus 1 only, because the variation is only with respect to x direction. But here the variation is there in the x direction as well as in the y direction also. So that means, so your variation is there. If the variation is the x direction, I have m plus 1. Okay. Okay, I'm sorry. Yeah. So if there is if the variation is there, okay, 3 nodes are there in the x direction only, then I am going to have m plus 1, m minus 1. Okay. Then if it is in the y direction also, then I am going to have n. Okay, sorry, n plus 1. I'm sorry, n plus 1. Here n minus 1. Okay. So you should know this is delta y, this is delta x. M is in the nodes in the x direction, y is in the y direction. Okay. Here you can see the nodes. It is in 2D. So that is why here I will be having, when it is in the x, n will be same. M plus 1, m minus 1 minus 2 tm n divided by delta x square. When it is in y, it is going to be m will be same, n will be same, and I have m comma n plus 1, m comma n minus 1, m comma n. So that is there here. Okay. So this is a two-dimensional problem. But when you are solving this, here also you are going to have an algebraic equation only. Instead of 3 terms, you will be having 5 terms in the interior nodes. Okay. So that is the difference. Okay. Otherwise, the discussion is going to be same. But you are going to, here the solution, it is going to be on a area. Okay, so you know you are getting contour plots, vector plots, everything you would have seen in an area. So that is a 2D problem. But in a 1D problem, you will be getting in a line only. So that is the difference. Okay, fine. Now, so how to solve the problems, or how to go about the problem. So if it is in a steady state, okay, so you can even derive this equation. Okay, so if it is a steady state, you can derive this equation. Throughout this is how I started in the first class or about the numerical simulation. So here you would have seen, okay, so here you would have seen this is what we are doing when I am writing for the node M. Okay, so when I am writing for node M, so I am doing the energy balance and I am getting the final equation. Okay, so this is one more method of doing that. So when I am considering the node M, so I am taking what is the energy transferred in the left of the nodal volume. So this is nodal volume. So left, what is the energy transfer? So I am putting it in this direction. Okay. Similarly, in the right, what is the energy transfer? I am putting it in the opposite direction. Okay. So, but usually, heat will be flowing in one direction only. Either it will flow from this to this or from this to this. Okay. And this is a steady state problem. Okay. So that means this left heat will be equal to left heat if there is no heat generation. That is very, very important. Heat generation should not be there. Otherwise, both will not be equal. For the sake of understanding, I am telling you. So both, if both are equal, so what will happen? If both are equal, it will be like this. Okay, so it will be like this. Okay, so it will be like this. So I have this is the node under consideration. So this is the node what we are considering. So heat is flowing in this direction. Similarly, heat is flowing in this direction. Okay. So previously what I told m plus 1 dou t by dou x here, m plus 1 minus m. Okay. Then we put the minus of m minus tm minus 1. So that's how we put it. Now what we are doing, the flux we are reversing the direction of the flux. Previously this was also moving in this direction, this was also in the moving direction. Now what I am doing, the same flux I am putting it in opposite direction. I am putting m plus 1 minus of m, Ka Tm plus 1 minus of Tm divided by delta x. Similarly, Ka Tm minus 1 minus m divided by delta x. Okay, so that is how I am having here. So when I am reversing the direction, okay, now this will be like plus and this will be like minus. So when I add these two things, it will be equal to 0. So that is how you will be getting. So this value plus this value. If you assume that this is not there, okay, so you assume that heat generation is 0. So then it will be equal to 0. Okay, I am telling for your sake of understanding. So what will happen if heat generation is there? So that means then there is a possibility that these two will not be equal. Okay, since heat generation is there, this will not be equal. So that is how it is shown here. Tm plus 1 is different and Tm minus 1 is different. Otherwise, both will be equal. Okay, it will be symmetrical. Okay, simply if you want to understand whatever we did in the previous time, the energy balance. Now you are just putting it on the other side. Okay, just putting it on the other side. So usually we will be doing this for energy balance, for giving the boundary condition in the steady state problem, even in the transient problem also. So that is why this becomes important. Okay. So what you have to do is, if any flux is there, 3 nodes are there, any flux is there, what you have to do? Have the flux in one direction in this way, another flux in this direction. You add, it will be equal to 0. Okay. So that means you have to take it like this. You have to remember this arrow. This minus of this, that is m minus 1 minus of m. You have it here. Similarly, m plus 1 minus of m. Okay. So you add both the things, it will be equal to 0. Or you can add the heat generation term into it. That is how you have to remember. Just try to understand. You are getting, if you add also, you are getting the same thing. Okay. So just you can go to the previous thing. There we were separating and we are getting the same thing. Okay. But it is Tm plus 1 minus Tm divided by delta x, minus of Tm minus Tm minus 1 divided by delta x. Okay. This is how I am adding. But now what I am doing, I am putting both in the same direction. Okay. So that is how I am getting this. So that is how, because of adding, I am getting the same expression. Okay. So I think this will help us. So you may be thinking, why unnecessarily we are discussing this? This will help us in understanding or giving the boundary conditions. Giving the boundary condition in finite difference method, it is difficult. So it can always be done by energy balance only. Okay. So that is why I am spending time on this. Okay. So what is the use of this? You yourself, you can write your own code for your building energy simulation, like how we are done. Okay. So you can do the same thing. Okay. You yourself, you can generate the codes for your analysis. Okay. Okay, so that is now I was explaining that. Okay, so when both the heat flows are in the same direction, you are taking this value minus of this value is equal to 0. Okay, When both the heat flows are in opposite direction, you are just adding it, then you are getting 0. So that is what you have to understand. So this is T1 minus T2 divided by delta x. Okay, this is T2 minus T3 by delta x. But when I come here, it will become T3 minus T2 into delta x. So we are following this only. Okay, so we are following this only. So here we are taking the arrow mark. Okay, so here we are taking the arrow mark. Okay, so here we are taking the arrow mark in this direction and in this direction. Okay, so that is how we will be doing for energy balance also. Okay, okay, so now you consider the wall. Okay, you think that our wall is there. Okay, whatever, yesterday also we have discussed about solution for the wall. So you think that our wall is there. Okay, what is the wall? So heat transfer wall or building wall is there. So inside that you'll be if you want to solve this problem, how will you do that? So you have to divide the domain wall, one-dimensional domain wall, into number of regular shaped divisions. Okay, so these are called grid points. Okay, so on all the grid points, I will be having the algebraic equation. Okay, so inside all the how to generate the algebraic equation, just now we have seen. Okay, for the conduction, one-dimensional conduction problem, how to generate the we have seen. Okay, now what are all the different types of boundary conditions that are possible? Okay, the type of boundary conditions that are possible are, so we have the specified temperature boundary condition. Okay, so that is called as boundary condition of first kind. You can just tell the temperature or specified variable. That is the first kind. Okay, and so for example, in this problem you can see here 35 degrees is given, here 82 degrees is given. This is prescribed temperature boundary condition. So it is called as boundary condition of first kind. Okay, and the boundary condition of the next kind, it is also called, that is prescribed flux. So just here you can see what is prescribed flux. So we are just giving the heat flux in one value. So you take the same wall is there. Okay, same wall, left surface there is a heat flux you are giving. For example, radiation is there. Okay, radiation is there from the atmosphere. Sun radiation is there. You are giving a radiation as the boundary condition. Okay, so how I can give that? Okay, so I am going to have a number of nodes. So you know this node. Okay, so for example, if I am taking node 1, it is going to have full volume. Similarly, node 2, it is going to have full volume. When I come to node 0, boundary node, it will always have half the volume. Okay, so now there is no other go, because you have to put a node at the boundary. There is no other go. If you want to put a node at the boundary, you will have half the volume only. So that is why you will have delta x by 2 here. But here it will be delta x. This distance will be delta x. Okay, so that we should know. Okay, so that we should know. Okay, and okay, now how you are going to solve the energy problem? Okay, so how you are going to solve this by energy balance problem? So here you can see I am giving the heat flux in this direction. Okay, so the heat flux. Okay, just 1 minute. So heat flux I am giving it in this direction, and this flux I am taking it as Ka into T1 minus of T2. Okay, Ka into T1 minus of T2. This I am taking in this direction, T1 minus of T0 divided by delta x. On this side, what I am having? Q. This is what I am having here. So Q left surface. Okay, so both I am adding. Okay, both I am adding plus heat generation. In heat generation term, you will be having the volume. So usually interior and all you will be getting delta x. Here you can see it is you are getting delta x by 2. So what is the reason? This is the reason. For boundary node, half the volume will be there. So that is how you are getting that. Okay. So from this, okay, it is possible for us to give a heat flux boundary condition to a finite difference problem. For example, if there is a wall, at the end, if you want to give heat flux, you can do so by this formulation. Okay, at the left surface, just your you may ask how you are balancing this, because this is also a flux only, and this is also a flux. What is the unit of this? Okay, this is Ka dt by dx. This is watts. Okay, and here this is not watt per meter square. Okay, it is watts only. Okay, it is not flux. I should not call it as flux. It is watts only. It is energy. So I am doing by energy balance. So this is watts. Okay, and here also you can see this is watts. This is watt per meter cube multiplied by volume. It is watts. So throughout it is watts. I am doing energy balance and I am trying to get a algebraic equation. By energy balance, I am getting an algebraic equation for node 1. And one more thing I need to tell. So if you are having a prescribed temperature boundary condition, so that equation will be eliminated from the problem. For example, at T naught is equal to 35 degrees centigrade. So that means you need not solve that equation. Okay, only interior nodes you have to solve. Okay, T naught is equal to 35 degree itself, it is a solution. Similarly, Tm is equal to 82 degrees centigrade is also a solution. So that means those equations, algebraic equations, you can remove. Okay, only you can write the equations for interior node. But on the contrary, when you are having the flux boundary condition, you have to give the flux value. Okay, you have to give the flux value, and you will be having an equation for node 0. So here you can see, here you will be having an equation for node 0. But when you are going for node 1, what is the equation? It is T2 plus T naught minus 2T1. Very simple. Similarly, when you go for T2, T3 plus T1 minus 2T2. So minus 2T2. Okay, so that is so interior and all it is easy. But when you are coming here, for boundary condition of second kind, the boundary node also will have an equation. You have to solve that simultaneously. That just put it in your mind. Okay. Okay, fine. Next we will see what are all the various other boundary conditions. Okay. So similarly, you think that on this side, okay, instead of heat flux, okay, so here you are having heat flux. No, instead of heat flux, I am having convection here. So what will happen if I am having convection here? Okay. So if I am having convection here, so I am going to have H here, T infinity here. Okay. Here I am having T naught. So how I can do the energy balance? So it is going to be H into T infinity. From this direction only I have to go. So T infinity minus T naught. So here I am having T infinity, H into A into T infinity minus T naught plus K into A into T1 minus T naught. T1 minus T naught divided by delta X plus the heat generation term is equal to 0. So remaining things I think it is. So here also you are generating an equation for T naught, because usually T infinity will be given in any problem. So that will go to the boundary condition. This will go to the boundary condition. But T naught is unknown. Okay. So even if you have heat flux, T naught is unknown. Even if you are having a convective boundary condition, T naught is unknown. So that means you are generating one algebraic equation. Okay. So next, if I am having a radiative boundary condition, what will happen? If I am having a radiative boundary condition, what will happen? So in a radiative boundary condition, so you have to replace this convective flux by radiative flux. Okay, so just you have to replace this convective flux by radiative flux. So what is a radiative flux? You know, it is given by Stefan-Boltzmann's law for real surfaces. It is a sigma A T surface power 4 minus T naught power 4 multiplied by emissivity for real bodies. Okay, so this is in watts, you may be knowing. So here also you have to take a surrounding minus a T naught. Okay, if you are taking a T naught power 4 minus surrounding, it is wrong. So always the flux should go from this direction towards the node. For whatever node you are writing, the arrow should go towards the node. That is how you have to do it for energy balance. Okay. Suppose if I am having combination of convection as well as radiation in a node, that is usually possible. In our wall and the exposed surface, you will have both radiation as well as convection. So that is possible. So that means if both are present, my equation is going to be like this. Here also order is very important. I have to go from T infinity to T naught, T infinity minus T naught, HA into T infinity minus T naught. Similarly, epsilon into sigma into T surrounding power 4 minus of T naught power 4. So that is how I should have in watts. Okay, plus Ka into T1 minus T naught plus this is the watts what I am having. Okay. So this is for combined convection and radiation. You can have next you can have for a combined convection, radiation, heat flux boundary condition. That is going to be same. Okay, that is going to be same. Okay, so that is this is also possible. Sometimes it is possible in a wall. Okay, a wall can be heated apart from convection and so. So here also the same thing. Okay, so it is obvious. So I'm just leaving it. Okay, same like that. Just you are adding this term. Okay, so that is how compare. So all these boundary conditions will be leading one equation. Okay, it will be leading to one equation. So one more important thing, what you may have it in your building wall is that you may have a non-homogeneous conducting material. So that means you may have brick, plaster, and insulation material. So all these things are possible. Or you may have some air cavity inside. So that means homogeneous material, non-homogeneous material, it is possible in a building. So how you are going to handle that? So that is being handled by. So the same thing. Okay, so this is the this mostly it will be happening inside. Okay, this is mostly it will be happening inside node. So this is a material having Ka, material A with the thermal conductivity Ka, and this is material B with the thermal conductivity B. So how it is happening? So it is happening same like energy balance only it is happening. So it is Ka into Tm minus 1 divided by Tm divided by delta x plus Kb into A into Tm L plus 1 minus Tm divided by del x. Okay. So these two things, okay, just I am getting added. So what is the difference? The difference is just this Kb is there here and Ka is there here. So at this point I am having a Ka and at this point I am having Kb. So that is the difference. Otherwise it is going to be same. And since it is interior, okay, since it is interior, you are going to have your node here. But what about the material? So material half will be from this because your separating point is here, okay, at the node. Your separating point is there at the node. So that is why in the heat generation term, so heat generation for material A, it will appear separately, okay. Similarly, heat generation for material B appears separately. So that is the difference what you are having, okay. So all the other things it is obvious, okay. So it is available in the thing, so you can just go through. So this is what we have discussed already. So conduction, convection, okay, conduction, convection put together, how the discussion is going to be, and how you are going to handle the insulation boundary condition. Suppose there is an insulation in the at the edge. So this is the wall. At the outside surface of the wall, you are having insulation, okay. Suppose if you are having insulation on the outside surface of the wall, so this is the insulation, how you are going to handle it. So mathematically insulation, it is given by dt by dx is equal to 0. So that is what you are going to have. From this equation, how you can get it, okay. So we are going for mirror image concept. The same thing we are going to get, but by mirror image concept. What is mirror image concept? Okay. So when there are 3 nodes inside the wall, you create a fictitious nodes 1 and 2 outside the wall. Okay. So this is the wall 0, 1, 2. So here you create a fictitious nodes 1. So there is no 1 and 2, but I am creating a fictitious node with the equal distance, and I am giving it here. And after that, what I am doing? So you know, this is the mirror. Okay, along the mirror, these nodes will be at the same distance. Now what I am going to do is, I am going to write this equation. I am going to write this equation. So when I am writing for node 0 along this, so what will happen? M plus 1 is equal to Tm minus 1. Tm plus 1 is equal to Tm minus 1 because this is also T1, this is also T1. So what I am going to have, Tm plus 1 becomes T1 here, and Tm minus 1 becomes T1 here. So this will become 2T1 minus 2T0 divided by delta x square. Okay, so that is how I am going to have. So it is almost like dt by dx is equal to 0 only. Okay, so we are trying to accommodate the insulation boundary condition. Sir, what if I am going to have discretize this one directly? So I am going to write this as a T of 1 minus of T0 divided by del x. I am going to write like this. Sir, is this correct, sir? Yes, it is correct. No problem. Okay, this is also correct. This is also correct. Okay, but here the accuracy will be more because it is second order discretization. It will be more accurate. So here the accuracy will be less. Sir, should I not use this one? You can use, no problem. Okay, this is the discretization of this, and you can always use that. Okay, now that we have seen the boundary conditions, what it can be applied for a wall problem. Okay, at various conditions. Okay, so there here you can see there is a simple problem which is given. Okay, so I told you, some you were telling that you have some trouble in understanding. So that's why I'm taking this topic. Okay, so this is a wall. Okay, in the wall you are trying to find the temperature distribution. Okay, so I'm having the wall. I am dividing the wall into 3 nodes. So one is node 0, node 1, and node 2. Okay, so for what is the boundary condition? So at this surface it is T0 is equal to 0. So that means I can eliminate this equation. T1 I have to write the equation. T2 also I have to write this equation. And this side I am having convection. So convection values will have been given. So the domain length is 40 centimeter. That is 0.0 sorry 4 centimeter, 0.04 meter. So the 2 centimeter, I am dividing this into 2 centimeters. Okay, so this is 2 centimeter and this is 2 centimeter. Okay, and I'm writing the equation for this node 1. T naught is equal to 0 itself, one equation. So it is solved. So you do not consider this. So for 1 I am writing. What is the, how I have to write? Tm plus 1, that is T2 plus T naught minus 2T1 divided by delta x square. So that is what I am having. T naught minus 2T1, T naught plus T2 minus 2T1 divided by delta x square plus E1 divided by K is equal to 0. So that is what I am going to have. Okay. And this is my algebraic equation. I have converted my differential equation into algebraic equation for node 1. Okay. In this also T naught you can substitute at 0. So your equation for the node 1 is 2T1 minus T2 is equal to E delta x square by K. E value and all it is given. You can just take it the values. Okay. Similarly for node 2, how I have to do? So put the arrow in this direction. Here you have to put the arrow in this direction. So H into T infinity minus T2. HA into T infinity minus T2 plus KA into T1 minus T2 divided by delta x. Okay, plus EA delta x by 2. And you have to know here the nodal volume will be, delta x by 2. Here the nodal volume will be delta x. Okay, here the nodal volume will be delta x by 2. Here the nodal volume. So that is how I am having. So I have to substitute. Okay, I have to substitute. Okay, so here you can see, here he is taking delta x square. Here he is doing EA into delta x by 2. Okay, so here you can substitute this. Okay, so you can substitute this and you can get the solution. Okay, so you can substitute the, so you have generated 2 equations. So how many nodes are there? 2 nodes, 2 equations. You can solve this to get the solution. Okay, so there are various methods for solving this. You can go by matrix inverse method, or you can go by simultaneously you can solve this directly by simultaneous equation, or you can go by Cramer's rule. You can go by iterative method. Okay, so many methods are there. Relaxation methods are there. Okay, so upper lower triangular matrix. So I am talking about big matrices. Here only 2 by 2 is there. It is a baby problem. Okay, so this I am not talking about this. If you want to solve a very big problem, very big problems, then you have to go for solution procedures, algorithms for solving big matrices. Okay, and so this is the problem. Okay, so this is the answer. Okay, so this is the temperature. Okay, you have the exact solution also. You can compare. Okay, you can compare with the exact solution, and you will be getting the result. Okay, so the exact solution is 136, and T2 it is 136.1. So this is how we will be solving a problem. So this is how we will be solving the problem. Okay, so we will be solving the problem. Okay, and okay, so this is how we will be solving the problem. So I find we will be generating equations. Okay, so the equations will be very big equations. Okay, so if you have 10 nodes, then the size of your matrix will be 10 by 10. Your size of your matrix will be 10 by 10. Then you have to solve by direct methods or iterative solvers. Okay, so direct methods I have told you, inverse method, Cramer's rule. Iterative solvers, you can go for Jacobi, okay, Gauss-Jacobi or Gauss-Seidel method. Okay, so these 2 methods you can solve further. So the matrix will be like this only. If it is a very big matrix, it will be like this only. Since for each equation you have 3 coefficients, so here you will be having 3 nodes. 3 coefficients only. So it will be a tridiagonal matrix. So if you are solving a one-dimensional problem, it is going to be a tridiagonal matrix only. So that means if all the energy simulation solvers for wall problems, you are going to have tridiagonal matrix only. Okay. Now this is the temperature distribution in all the nodes. So when you try to solve this D, you can take this to the other side, A inverse into D. All your boundary conditions, it will come in this place. When you solve that, you will be getting the temperature distribution at all the points. So using the temperature distribution, you can find out what will be the heat transfer in the wall. Okay. So and you can solve by Jacobi method also. Jacobi method, what you will be having? You will be taking the equation. Okay. So you will be having just now you have seen these equations will be like this. So here there are 5 equations are there. 5 equations are there. They are trying to solve 5 equations. How they will be solving in the Gauss-Seidel problem? In CFD, mostly you will be using Gauss-Seidel problem only. Okay, so that means you need to know about a Gauss-Seidel procedure. So in a Gauss-Seidel procedure, so you'll be having a lot of linear algebraic equations. So for each node, I'll be having these equations. So what I have to do, I have to come with a guess solution for this problem. I have to come with a guess solution for this problem. So that means I will be having a guess set for T1, T2, T3, T4, T5. So that means give those values and try to find out the new values. So for example, here you can see he has come with 195 throughout. T1, T2, T3, everything he has taken 195. Then after that he is again calculating T1, T2, T3, T4, T5. Okay. So that means he is calculating all these values. Okay. So after solving this, then next time he will go with this value, and again he will go to calculate what is T1, T2. So that means every iteration finished. So you will be getting one set of T1, T2, T3, T4, T5. So when it will converge, so here you can see after 3, the value is not changing. This value is not changing. This value is not changing. This value is also not changing. This value is also not changing. So that means the solution is converged. Okay. So that means if between the present iteration and the next iteration, if there is no change, okay, so then we call the solution is converged. Okay. So that is a Gauss method. What is the difference between Gauss-Jacobi and Gauss-Seidel method? In Gauss-Jacobi method, so you will have a set of guess value. You will have a set of guess value, and you will calculate all the values. Okay. You will calculate all the values. Then only you will go for the same. That means you will have a guess set. You will have a calculated set. This calculated set, you will take it, and again you will do the calculation. So like that, it will proceed. But in Gauss-Seidel problem, what will happen is you will calculate T1. Okay, so you will calculate T1. So this T1 immediately you will be using in the next iteration. Similarly, you will calculate T2. Immediately you will be using it in the next one. So similarly, T4, T3, immediately. So that means if you are using the calculated value immediately within the iteration, immediately the next in the first iteration set. So that is called as Gauss-Seidel method. So that means the convergence in the Gauss-Seidel method will be faster compared to Gauss-Jacobi method. In Gauss-Jacobi method, one set will be there. Okay, you will calculate fully with the same set only. Then again you will substitute and you will calculate it. So you will be going on iterating until you will get the converged solution. Okay. So usually in the CFD solvers you will be having a Gauss-Seidel iterative solver only. Okay, I will tell you the reason. Okay, so as the time goes, so I will tell you the reason. And sometimes you can go for relaxation factor also. What is relaxation factor? So you have calculated some value. For example, for a particular node, you have calculated the value as after one iteration, you have calculated the value as 35 degrees centigrade. So previously the value was 34 degrees centigrade. Okay, so that means now the present value is 34 degrees. For next iteration, the initial value, if you want to take, so you have to take 35 degrees. Okay. But if you are taking, sometimes it happens that if you are putting 35 degrees from 34 degrees, so the solution will not converge. So there will be a trouble. So what you have to do in that case is, instead of rising by 1 degree, you can reduce. Okay, for instead of going from 34 degrees to 35 degrees, you can go from 34 to 34.5. So what is then at that case? What is your relaxation factor? It is 0.5. So this is the value calculated by Gauss-Seidel. This is what the present value. This is like 34. I mean 35. I'm sorry. And currently you are having 34. So what is your value? So you are taking it as 0.1. So 0.1 means it is 10%. So that means 0.1. If you take it as 0.1, so it will take it as 34. 35 minus that 34. It is 1 into 0.1. So 0.1. So the new value will be 34.1. So why, instead of going 35, why you are going for 34.1? If I go for 35, it will diverge. Okay. So if I go in steps of 34.1, it will be controlled and it converged. So this will be very much helpful if you are having a system of continuous linear algebraic equation. I'm telling systems of equation. That means you have sets of equations. For example, in CFD, you will have continuity, momentum, energy. Sometimes you will find one of the equation will be diverging. How to bring it back? So you have to make use of a relaxation factor only. So in the relaxation factor, you have to go and whichever it is diverging, you have to go and decrease the relaxation factor. So when you decrease the relaxation factor, then it will lead to the convergence. So that is the usefulness of relaxation factor. So Gauss-Seidel method is good. So if you want the convergence, okay, in the Gauss-Seidel method, okay, you can go for relaxation, because this will be useful particularly for the problems where you may not have solution. Okay, so where you may not have solution. So in the CFD, we will be telling that matrix. Okay, so matrix may not be consistent, or matrix may be uh, uh, matrix may not be conditioned. Okay, the condition number of matrix may be higher, so there you may not be having the solution. So if you go step by step, instead of going from 34 to 35, if you are going by 34.1, 34.2, then you will get the solution. But if you go in steps of 34, 35, 36, you will not get the solution. So there this will be helpful for you. Okay. Okay, so you have the arbitrary shaped domain. Okay, so you have the arbitrary shaped domain. You are dividing that into regular shaped subdomain. For each subdomain, you are having meshes or grid points. For each grid point, you are trying to solve the problem. You will be getting the solution. Okay, you will be getting the solution. So this is how you will be having the steady state solution. Okay, and today whatever we have discussed, it is one-dimensional problems. If you are going for the actual CFD, okay, so the domain will be like a volume. So here you can see we are considering a building. Okay, so you are considering a building. Okay, so here you can see. So it is a building. Okay, so you are having a building. So here you can see. Okay, so the building shape is like this. So we are considering air is flowing in this direction. It is an external analysis. We are trying to find out what is happening, okay, inside. Okay, so what is my domain here? My domain is here is fluid. In CFD, the domain is fluid. In the energy simulation, the domain is solid. In finite element analysis, or if you are going for a structural problem, the domain is a solid. If you are going for a wall problem, domain is a solid. If you are going for a CFD problem, the domain is a fluid. So here the air which is blowing over the building, so that is the fluid. Okay, so that is the fluid. So that is the domain. Okay, so we want to find the response of that domain for the external excitation. What are the external excitation? The boundary conditions we give. So we are giving the boundary condition. Here we are giving the velocity. Okay, velocity inlet and velocity outlet we are giving. We are giving the direction of velocity. Okay, and we are solving that. Okay, we are solving that. Okay. After solving that, so we are dividing that domain into number of regular shaped domains. Those subdomains are called as mesh. Okay, and after and then I am running the solver. Okay, then I am running the solver. After running the solver, I am getting the solution. So from that I am plotting. Okay, so I am plotting the solution. So then I am getting the solution. Okay, so here you can see this is a solution. Okay, so this is a velocity plot. Okay, so this is the velocity plot. So I have considered that building. Okay, so I have considered the building. So I am taking a CFD. For the CFD, I have given the boundary condition. I am giving velocity inlet. So when the thing is increasing, okay, so when the fluid velocity is increasing, okay, so I am giving velocity here. When it is falling on the building, when it is coming nearer to the building, you are finding that the velocity is decreasing. Okay, because in this place pressure will be increasing, so the velocity is decreasing. And since you have taken the domain like this, so the air will be moving in here. So it is giving an acceleration effect there. But in reality, there will not be an effect like this, because I have to take a very big domain. Okay, so then only this velocity will not be there. Over the building, this high velocity will not need not be there. It is there because from a larger area you are going to a smaller area, and you are restricted to the domain here. So that is why you are having that acceleration, high velocity here. How to see the velocity? So if I'm having a higher red color, okay, so from red color it will decrease, it will go to up to blue color, okay. So that means 15.76 meter per second, that is the maximum velocity I'm having, and 0 is the lowest velocity, and it will go from red, okay, to the blue color. Okay, so that is how. So wherever I have this red, orange, and all, it is higher value. Yellow next, green, and after that blue and dark blue. That is the lowest value. Okay, and this is the velocity plot. Okay, this is the velocity plot. So similarly, okay, similarly I can find out. Okay, similarly I can find out what will be the uh, uh, I can find out what will be the. So here I have put field velocity contours. So similarly, I can put field pressure contours also. Just to note, just to keep these details in your mind. Okay, so we will try to find out what will be the pressure plot in this area. Okay, you will find that will be complementary. Okay, wherever velocity is more, pressure will be less. Wherever pressure is less, velocity will be more. Some of you can tell me what is the reason. Okay, if any of you know, you can unmute yourself and you can tell the reason. Okay, so I'm telling that wherever in the velocity plot, wherever the velocity is more, okay, the pressure will be less. Wherever pressure is more, the velocity is less. Okay, so that is what the statement I'm telling. But it is not applicable for all the places, but some specific places it is applicable. Okay, so that if you know the answer, you can unmute yourself and you can tell. So I will show the pressure plot. Okay, so I will show the pressure plot. Okay, so now okay, so I will put the slice. Okay, so now here you can see here the velocity was more. Okay, so now here the velocity was more. So here the velocity was more. Okay, so now you are, what is that you are finding? Wherever the velocity was more, now the pressure is less. Here the velocity was less, pressure is more. Okay, in this place you are finding both the pressure and velocity is less. So anybody, you can tell the reason for this. So it is an open question for everyone. Okay, anyone who can tell the answer for this? Okay, so if you are not telling, I will tell the answer for that. So just for the sake of understanding, I ask. Okay, so it's very simple. It is Bernoulli only. Okay, so you know the sum of the pressure energy and the velocity energy will be constant. So if some places, if velocity energy is increasing, okay, so the pressure energy will be decreasing. Or in some places, if velocity energy is increasing, pressure energy will be decreasing. So here what you are finding, okay, so in this point, because of the air hitting on the building, so the pressure is rising at this point. So when pressure is rising, you found in the velocity plot this place the velocity was less. Similarly, you have found that there was acceleration velocity, high velocity in this place. But in this place, now you are finding that there is no high velocities. The pressure is decreasing. When velocity, wherever velocity was more, pressure is decreasing. Okay. So again, same reason, Bernoulli. It is because of Bernoulli. So, but one place where the Bernoulli will not be satisfied, it is because of the wake behind the building. Behind the building, you will be having the wake. So once again, if you want, we can go and see the velocity plot. Okay, so we can go and see the velocity plot. Okay. So now you can see the velocity plot. What is that you are finding is okay. So okay, both are coincident. Okay, I'll remove. So this is a velocity plot. What we have found out. Okay. So in the velocity plot, what we are finding is the velocity is increasing. Okay. So the velocity is whatever the boundary condition we are given, it is existing here. Okay. So I think I can put one more slice here. Okay. So I will remove this. Okay. Yeah. So here you can see that I can put here. Here the velocity is decreasing. Okay, velocity is increasing here, and here velocity is decreasing. Behind the building, the velocity is decreasing. Okay, so that is what you are finding. Okay, and behind the building, the pressure is also decreasing. So that is the difference. What is there? This is called as wake behind the building. Okay, so wake is like a vacuum. Okay, vacuum means less pressure region or less energy region. So you cannot apply Bernoulli's equation in a less energy region. Okay, you cannot in the wake you cannot apply Bernoulli, but you can apply in this region, potential flow region. Okay, here and all it is potential flow region. Here you can apply. So you have found that here velocity is less and here velocity is more. So in the pressure plot, okay, so in the pressure plot we have found, okay, in the pressure plot. Okay, so again it is showing velocity plot only. Okay, I'm sorry. So I should put the field pressure contours. Okay, so that's why it's not showing. Okay, so I'll remove the slices. So I'll, okay, so this is how it is. Okay, now you can see wherever in the front of the building I'm having high pressure. Okay, so that is how I am saying Bernoulli's will be satisfied here. Okay, what is Bernoulli's equation? The sum of the pressure energy and velocity energy plus the datum energy will be constant. Datum is not applicable here. Sum of pressure energy and velocity energy is constant. So wherever pressure energy is more, velocity energy will be decreased. Wherever velocity energy is more, pressure energy will be decreased. But the behind the building, it is a vacuum region. It is not perfect vacuum region. It is a vacuum in the sense low pressure region. So there Bernoulli's will not be satisfied. So that is why I'm getting this. Okay. So now I'm getting the pressure plot. I'm getting the velocity plot because it is a flow problem. Okay. So in the flow problem, I have two. I will be having a momentum equation and the continuity equation which I will be solving. So because of that I am getting two plot. Okay, in momentum three velocity plots are possible. So x velocity, y velocity, z velocity, it is possible. Okay, so that means how many number of equations we are solving, so many number of plots I will be getting. Suppose if I am including energy, I am doing internal analysis, there energy will be coming. So if I am solving energy equation, then I will be getting one more plot for temperature also. Okay, I will be getting one more plot for temperature also. So that means there also I will be getting. Okay, so how many number of equations I am getting solving, so many number of plots I should get. So that is CFD. Okay, that is how we will be getting. But today whatever we have discussed about only one physics, that is the energy equation alone. In that we have discussed about the steady state alone. Okay, for the first case I am taking steady state alone. Okay, so and we have seen that we have see the so how we are getting various plots with various equations. So that is what we have to understand. So with that we will close our discussion. Just 1 minute. Okay, so my transient discussions we will have it. Yeah, so we will have it. Okay. So I have the governing equation. Okay, so I have the governing equation. So this is the general transport equation for CFD. Okay, so maybe tomorrow we will discuss this topic. So this is the general transport equation for CFD. So here when I am trying to solve this general transport equation, so a phi, okay, if I am varying the value of phi, so I'll be getting various equations. For example, if phi value is 1, so I'll be getting continuity equation. Phi value is u, x momentum equation. Phi value is b, y momentum equation. Phi value is w, I'll be getting z momentum equation. And if I am having a enthalpy, left hand side enthalpy, right hand side temperature, it is energy equation. If it is concentration, that means it is a species equation. So that means here in the how, if I include all the physics, I will be getting all the plots. For example, if I include all these things, I will be getting energy plots, species plots, everything I will be getting. Okay, if I am not including, I will not be getting the plots. So in this problem what I have taken, so I have taken the continuity equation. It is a 3-dimensional problem. So first, please understand, it is a 3-dimensional problem. I have taken the continuity equation, 3 momentums equations. Okay, so that means I will be getting 4 answers: x velocity, y velocity, z velocity or z velocity, and pressure. Pressure plot is corresponding to continuity. How we are getting all these things? Okay, so that we will discuss in the next class. Okay, so again I am telling in the CFD, so we will be having a domain. So the domain will be a fluid. So we will be dividing the domain into number of regular shaped subdomains. Okay, so we will be dividing the domain into number of regular shaped subdomains. Okay, So that regular shaped subdomains, it is called as meshes. For each mesh, you will be having the governing differential equations. It is not one equation as we have seen today. So you will be having four or five equations, and depending on the problem. So usually in building problems, for flow analysis, external flow analysis, you will be having four equations. Plus, if at all k epsilon equation is there, that equation also it will be there. Okay. If you are going for the uh, internal analysis, their thermal problem also will be solving. So that means you will be having one continuity, three momentum equation, one thermal equation, plus k epsilon equation. So you will be solving 7 equations. Okay. So you will be getting 7 plot. You are supposed to get 7 plots. And even at convergence also. So this problem, it will not be solved just like that. Okay. So we have to iterate. Okay. Then only finally you will be getting. Maybe tomorrow we will see how we are iterating and how we are creating the domain, how we are iterating, and how we are getting the solutions that we can see tomorrow. Okay. So that point we will understand. Okay. So how this? So all these things we will discuss tomorrow. Okay. Thank you. With that, I am closing. So we will continue our discussion tomorrow. Okay. Thank you, everyone. Thank you for joining. And any doubt is there, you can put it in the chat box. Okay. PPT not changing. Okay. What is your paper name? My paper name is there given here. Okay. Contribution of dry indoor condition, airborne coronavirus. Okay. 1 minute, I'll put it in the chat box. Is there some problem in the PPT? PPT is not changing, it seems. Dyagarajan? Some problem was there in the PPT?
No, sir.
Okay. Any other question is there? Regarding today's discussion, any other question is there? No question is there? Okay. Everyone, are you there?
Yes, sir. Audible. No.
Yeah. Okay. Tomorrow we will have a discussion on CFD. Okay. That is maybe transient. We will have a small discussion for some time, and after that we will have a discussion on CFD. Maybe for CFD I can work out some problems in DB, design builder. Okay. So I can work out some problems on design builder. For CFD alone I can do that. Okay. I can do that. Yeah. So any other question is there? You can put it. Okay. So you can put it in the chat box. So if no question is there, then thank you.
Thank you, sir.